short break of 1 week. So I was at that conference. So that's why I am not able to take classes last week. But anyway, today we will start by this topic, that is power system stability. So before I start, the previous class what we have done was closing of the topic of unsymmetrical faults. So today I try to start this topic, that is power system stability. So let's begin our talk today, and then if you have any doubts, you are always feel free to ask the doubts. In the participants list, there are not many colleges listed. So so can we start, or should we wait for more system stability? So this is just one lecture. So normally power system stability is like a full course. So but then today we are going to just see very basic overview of this topic. So we cannot go in depth because power system stability is actually a full course. So let me just give you an idea what we mean by power system stability. So in order to understand the power system stability, first we should understand what is the working principle of a synchronous machine. So it could be a synchronous generator or synchronous motor. How a synchronous machine works, what is the working principle, we'll just quickly review. So based on the working principle, we can define what is stability. So working principle of a synchronous machine. So let's talk about synchronous generator. So you have, or synchronous motor, because motor is more easier to understand. So you have the lines. So this is A phase supply, B phase supply and C phase supply. So three phase voltage supply is balanced voltage supply is available. Then you have the stator. So this is the stator. So by the way, this is a power system course, but then you normally study this in a machines course. So this is the stator of a three-phase synchronous machine. And stator will have, let's say, A phase winding and then B phase winding and C phase winding. I'm just only very roughly giving you the winding description. And all of them are connected. So let's say these are the terminals. This is the A terminal, B terminal and C terminal. So A is connected to the A supply line, B is connected to the B supply line and C is connected to the C supply line. So this is B. So as a result, what happens? So as a result, a rotating magnetic field is set up. So three-phase supply results in rotating magnetic field. In the air gap. So this is the air gap. So inside this air gap, a rotating magnetic field is set up. So what is the direction of the field? So let's say the direction of field is like this. So this is North Pole, this is South Pole, and a magnetic field is going downwards. But then this is not a stationary magnetic field, this is a rotating magnetic field. So after a while, the magnetic field will rotate and then you will get this direction. So in fact, I'll just write only one. So this is Fs, magnetic field of the stator. So this side North Pole and this side South Pole. This is just like a rotating magnetic field. After again some more time, again you will find like this. After some more time, you will find like this. After some more time, you will find like this. So if it is a two-pole machine, you will keep finding that the magnetic field is rotating like this. That's because of this one. So what determines the speed of rotation? So speed of rotation, Ns, is 120 F by P. So if you have higher frequency of supply here, then the synchronous speed will be more. So this is in revolutions per minute, RPM. So if depends on the poles. So the winding which is there is wound in such a way that particular number of poles are predefined. So it could be a 4-pole winding, it could be a 3-pole winding, or it could be a, sorry, not 3-pole, it's an even number winding. It's a 4-pole winding or a 6-pole winding or a 10-pole or whatever even number of poles of winding. So now, therefore, if you conclude the discussion, what you can say is the stator is nothing but yeah, it's already imagining. So it's a north pole and a south pole. Two magnetic poles are there. You just imagine these two poles, which are rotating at the speed of ns, synchronous speed. So this is what is this one. So there are no actually physical magnetic field is not magnetic poles are not there, but there is a magnetic field uh, which is rotating at a synchronous speed. So what is ns for two-pole machine? So 120. If you assume frequency is 50 hertz and the number of poles are 2, so this will be 60 and then this will be 3000 revolutions per minute. So in 1 minute, the North Pole and South Pole together, they will make 3000 revolutions. That is the speed of the this one. So for all practical purposes, let's consider stator as like this. What about rotor? Now coming to rotor, so rotor is like this. So rotor has a north pole and a south pole. So it's a two-pole rotor. So it should be a two-pole rotor, and then there's a DC winding. So it's a DC. So whenever DC current flows through this winding, a DC magnetic field is set up, and then magnetic poles are there. And since it is a motor, so the magnetic poles, there is a shaft coming out of it, and then there is some mechanical load. Some mechanical load. So some mechanical load is available here. So now put the rotor and stator together. So we find, by the way, what is the rotation of this? Right now there's no rotation defined. I'm just, so initially you consider it is on no load. The magnetic field is energized. That means I start circulating the current in the rotor magnet, and then the rotor magnet is energized. So together we have a north pole and south pole for the stator, and then we have a south pole and north pole for the rotor. This is how they lock. So this is called magnetic locking. So south pole of the rotor is attracted to the north pole of the stator. North pole of the rotor is attracted to the south pole of the stator. Again, this north pole and the south pole are only imaginary. Actually, there is a rotating magnetic field. So this is rotating at a synchronous speed of ns. Sorry. Now, because this attraction is there, this is also rotating at a synchronous speed of ns. So, which is equal to nr. So, nr is the rotor speed, which will be equal to the synchronous speed, and then they are rotating. Similarly, here also, this is rotating at basically it's the same thing. So, there is a magnetic locking. So, very, very important concept, magnetic locking. So, because there is a magnetic locking between the rotor poles and the stator poles, the rotor always rotates at synchronous speed. That is the feature of a synchronous machine. In fact, the name itself is synchronous. So the name itself is given like this because the rotor and stator are in synchronism. Either it rotates at ns equal to nr, or nr will be equal to 0. It does not rotate. So whereas the induction machine, if you compare, it is different. Induction motor actually slips. So there will be synchronous speed may be 3000 rpm and the rotor speed may be 2900 rpm or so, something like that. So there could be a slip concept. But here there is no concept of slip. Either the rotor rotates at the synchronous speed or it doesn't rotate at all. There is the concept of stability coming into picture. Whether the rotor is able to rotate at synchronous speed. Let's see what happens if I add a load. So let's say if I connect a load, some kind of mechanical load. We are talking about motor. So the moment you add a load, the load will have a load torque Tm. Mechanical torque will be exerted by the load on this shaft. So this torque will slow down the rotor. So momentarily rotor becomes, so when load is added, momentarily rotor slows down. So that means when the rotor slows down, so you get a situation like this is the stator north pole, this is the stator south pole, and the rotor will become like this. This is rotor south pole and this is rotor north pole. So this angle, so if I define this as the vertical as the reference for the stator magnetic field, this is the reference for the rotor magnetic field. This angle let us denote as delta m. So this angle is what will get created. Now, I said momentarily. That means momentarily it will slow down, but later on it will pick up its speed. Why it will pick up the speed? The reason it picks up its speed is there is some kind of magnetic attraction between these two poles, and also there is a magnetic attraction between these two poles. The attraction of the magnetic attraction actually increases if this gap increases. See, when it is completely aligned, North Pole and South Pole, there is not much of torque that is generated, the magnetic torque to do that. When you try to move it, it is like it's a rubber band. So when the rubber band is straight, it does not have much tension compared to you try to pull the rubber band like this. So you stretching the rubber band, it creates some kind of a force. So that it gets to the normal position. So similarly, just like how a rubber band stretches, it exerts more torque. So here also the more torque is generated. So as a result, what is happening? There is a load here. The load is applying a mechanical torque, whereas this electromagnet or whatever you can just define it as an electrical torque. So electrical torque is actually again trying its opposite, operating in the opposite direction, trying to align this back to this. So as a result, this will still there is still locking is maintained, and this is rotating at a synchronous speed ns. This is also rotating at a synchronous speed ns, which is equal to nr. So both are rotating at the same speed, but now some angle is maintained, that is delta l. This angle is proportional to the load that we are connecting here. So there is a load here. So if I increase the load, so let's say load is 10 newtons here. If I double the load, the angle also will double. How far is it possible? So it turns out that I can gradually increase the load. Gradually this south pole will keep on coming. Now at a point when these poles are exactly horizontal, there is some kind of a falling out of step happens. The magnetic lock cannot be maintained more than that. So there is a limit. We cannot load more than it. So that limit is what we are calling it as a stability limit. So I hope now you understood. This is the working principle of a synchronous machine I just explained. And then I explained why this angle is coming into picture because of the load. And then what is the meaning of falling out of step? If the load may be gradual or the load may be sudden. In the case of sudden load, there will be oscillations in theta m, and then finally it will settle. So far, do you have any doubts? Whatever I explained, the working principle of machine and all. Importance of the angle, that is the load angle. Now, what happens in a generator? So let's talk about this. So far, what we discussed is synchronous motor. Let's talk about synchronous generator. So in synchronous generator, there are two types. One is the generator which is grid connected, and the generator which is off grid. So let's discuss only the grid connector first. So these are the lines A, B, C, supply lines, and this is the stator. So, and then this is A, this is B, and this is C. So this is what happens in the stator as it is. So what is the effect of this? Rotating magnetic field is set up. So rotating magnetic field is set up in the state synchronous generator. So even the synchronous generator, when you connect to the grid, it will be like this. Now, what happens to the rotor? So rotor is exactly same thing. So let me just open a new file. Rotor is also exactly same. There is a magnetic field, and then there is a south pole and a north pole created like this, and there is a north pole and a south pole created like this. So this stator pole is rotating at synchronous speed ns, and this is also rotating at synchronous speed ns. Now instead of having a load, let's connect a prime mover. So a prime mover is connected. So for example, there is some kind of a turbine, and then there is some kind of a steam that is coming like this. So this steam is trying to rotate this machine like this. So in fact, I think I have shown the direction wrong. Let's say the steam is like this, and then this is mechanical steam. This is trying to rotate the machine. In fact, I think I have. In fact, let's say it is arranged that the rotation is like this. In R. So what happens is you are rotating the machine such that your NS and NR are there, but still there is a magnetic locking. So magnetic locking is still there, but then if I try to send more power, if I put more steam input or more mechanical input, then the NR will become greater than NS momentarily. So it will become greater than NS, and then you will get a situation like this. This is North Pole, this is South Pole. And then your rotor will move forward. So this is South Pole and North Pole of the rotor. And then this is moving forward. So here again angle is created delta M. So let's consider this as positive direction. So delta M becomes positive. Whereas in the earlier case delta M becomes negative. But still there is magnetic locking. Still the NR is equal to NS, but still some delta M is there. So the more mechanical input you provide, the more higher this angle will become. So that is how the generator works. So I'd like to summarize this entire discussion with a couple of diagrams. So the diagrams are like this. So think of this as a shaft. So this is the shaft, and then this is the rotor. So this is the rotor, and this is the shaft. Now on top of this, if you talk about a synchronous motor, then the mechanical input will be, mechanical power will be the output. The shaft will release mechanical power as the output and electrical power will be the input. And what about the rotation? So let's say it is rotating like this. So if I look from this side, it is rotating counterclockwise. So let's define the rotation as angular velocity omega m. So this is radians per second. It is rotating like this. Now the electrical torque, because of this electrical power input, electrical torque is created. So the electrical torque will be same direction as the rotation. Because electrical torque is what is trying to rotate the machine in this direction. Whereas the mechanical load torque will be in the opposite direction, Tm. So mechanical torque is opposite to electrical torque. Now, but then when Tm and Te are both equal, both the opposing torques are cancelled out, and therefore the omega m, whatever is the speed, that speed is maintained. So under steady state, what happens? The mechanical output power is equal to electrical input power. So that is not worrying about losses, or let's say losses neglected. And mechanical torque will be equal to electrical torque. And the speed will be omega m radians per second, which is equal to omega s synchronous speed. This is what happens in a motor. Now, let's talk about synchronous generator. So again, this is the shaft and this is the rotor of the synchronous generator. Stator I am not showing in this diagram. So the mechanical power will be the input. So there is a steam turbine, there is a or there is a water turbine, or there is a some kind of a mechanical input. That input is going to the shaft and the output is electrical power PE. Just the directions have reversed. If you compare with the previous one, the PE is going into the rotor and PM is coming out of the shaft. Whereas here, the PM is going into the shaft and PE is coming out of the rotor. Next, what about the speed of rotation? So let's say this is the speed of the rotation, and therefore the mechanical torque will be at the same speed or same direction as the rotation of the machine, whereas the electrical torque will be opposite. So if you go compare with the motor before, the electrical torque and the speed of rotation are in the same direction. That is because the electrical torque is causing the rotation in the synchronous motor, whereas here the mechanical torque is causing the rotation and electrical torque is opposing the rotation, and out of that opposition the energy conversion happens. So again, under stability we have PM equal to PE, and then we have Tm equal to Te, and we have omega s is constant. Omega s, or you can also say omega m. Omega m is a mechanical radians per second. Omega s is a synchronous speed, that is radians per second. But anyway, under stable conditions, both are equal. Okay. So any doubts so far here? Whatever I have discussed, I have just so far what I have discussed, nothing new. I have explained a working principle of a synchronous motor and a working principle of a synchronous generator. So I would like to give you a couple of minutes time. If you have any doubts so far, please ask the doubts. I'll just wait for a couple of minutes. Let's continue. So Coming back to this figure, here this rotor and shaft and everything, they are all mechanically very huge uh, items. So there will be a lot of weight and then they are rotating at a very high speed. So for example, for a two-pole machine, 3000 RPM. So in 1 minute, they make 3000 revolutions and it's probably in thousands of kgs or tons of weight. So a lot of energy is stored in that. So there's a lot of kinetic energy stored. So if you look at more simplified kind of a picture, so there is some kind of a kinetic energy stored in the machine, and then I am giving the mechanical power input, and then I am taking the electrical power output. So this is what is happening. So under normal conditions, when mechanical power and electrical power are equal, there is no change in the kinetic energy. But momentarily, if I push more mechanical power, first the kinetic energy increases and then finally the electrical energy increases and then again finally the equilibrium is maintained. So this is what is happening. So now I can ask a question. Consider a, consider a generator. Generator is connected to some bus bars and some mechanical power is input to the generator and the electrical power is coming out. And this voltage is V or let's say V1. Now if I there is a fault, for example, so I denote a fault with a switch. So I can control the switch. So if I close the switch, that means there is a fault. And if I open the switch, fault is clear. So if I close the switch for let's say 10 milliseconds, S is closed for 10 milliseconds. So during the 10 milliseconds, what happens to the voltage? So this is 0 volts, so the voltage becomes 0. When voltage is becoming 0, the power also becomes 0 because you know that the power is nothing but root 3 VLIL cos phi. If the voltage is 0, the voltage to current whatever, the power is also 0. So for the 10 milliseconds period, the electrical power is becoming 0. But mechanical power cannot become 0 during the 10 millisecond period because there is a heavy mechanical, there is a boiler, there is a steam is heated and then a high pressure steam is coming to the nozzle and all. The nozzle cannot move in such short time of 10 meters per second. So practically the mechanical power is constant. So as you see, what happens? So if I draw time versus the powers, so you will get mechanical power is straight. This is PM. Whereas the electrical power, it is equal first, then suddenly electrical power reduces, again electrical power goes back to this one. So during this time, some additional kinetic energy is provided to the machine. So that will result in increase of the angle delta. So delta increases. That is, delta is the angle between the rotor axis and the stator axis. Now, how much can the delta increase? So again, if I draw the diagram, this is north pole, this is south pole, and then this is delta. So if this is a rotor, south pole, north pole, and this angle between these two, this angle is delta. So if I close the switch for 10 milliseconds, maybe it is delta is slightly increasing. Again, it is coming back to normal position. It is still in stability. What if instead of 10 millisecond, I close the switch for 20 millisecond? So for more duration, the P is there. So more energy is imparted into the kinetic energy, and the delta will swing more. So finally at one point, so maybe 30 millisecond or 50 millisecond, whatever. So after a particular time, the angle theta becomes more than 90 degrees and then it will lose the synchronism. So that is what is the loss of stability. So I can give you another example. So think of think of a system like this. So it's a mountain and then there is a round stone here. Now if I push the stone, the stone will go here and then come back. So because slight height is there and then it will come back and then it keep oscillating here. But then if you push the stone with more force until the time that the stone comes up to here and then after that the stone will keep going, it will not come back. So this is the limit, this is the stability limit. So a similar question we are asking here, whether the fault it can withstand 10 millisecond fault or it can withstand 20 millisecond fault or it can withstand the 30 millisecond fault or so on. So how much milliseconds it can withstand? What is the time in which the fault has to be cleared? So it's another technical term is critical clearing time. So the question we can ask is, what is the critical clearing time? Something like this. So this is the what is the stability study involves. So that if I know what is the critical clearing time, that means the time before which stability is maintained and the time after which stability is lost. So I will try to maintain the, I will try to clear all the faults before the critical clearing time so that the machine is maintained under stability. So that is the problem that we are trying to do. Okay, so enough of generalized discussion. So let's get into some actual derivation. So you have any questions until now? So far, whatever we have discussed, any doubts until on that? Let's begin one important topic here, that is derivation of swing equation. So what we do now is we like to derive an equation called as swing equation. So swing equation is the equation which represents the variations in delta. So let's see what is this delta and all, we'll come to it. So go back to the diagram which I had drawn earlier. So let's define an angle. So if I define a vertical as the reference, from that how much it is rotating, that angle is theta m. So what is the unit of this angle? This unit is, since it's an angle, it is measured in radians. So we have like the we have something like this, F equal to ma. This is a Newton's law. This is just for linear motion. So what is this? So this is a net force that is acting on the body. This is the mass of the body and this is the acceleration of the body. This is for linear motion. Similarly, we have torque equal to J into alpha. So what are the things? T is net torque on the machine. Net torque on rotating object. So these two are very this one. So what is J? J is called moment of inertia. And then whatever this alpha is called angular acceleration. So F equal to ma is for linear motion. For rotating motion, we have this. So what is acceleration? Acceleration is meters per second square. That is the derivative of velocity, which is the derivative of position. So I can write it. So, but what is the net torque operating on the machine? So net torque operating is Tm minus Te. So there is a mechanical torque and then the electrical torque is opposing the. We are talking about the generator. So this is equal to J, and then this is the second derivative of the position of the this one. This is basically F equal to mf applied for a rotating object. So acceleration is nothing but second derivative of the position. Theta m is the position, and then this is the acceleration. So here I just like to use another variable. See what happens is theta m is the absolute position. Absolute position of rotor. With respect to stationary axis. So that means if there is this is a stationary, this is the rotor, this is the stationary reference. So this is the reference. From there, how much is the axis of this one is theta m, axis of the rotor, it is theta m. Now I want to use, instead, I want to use relative reference, moving at omega s. Omega s is the synchronous speed, that is radians per second. So instead of having a fixed reference, this is a fixed reference, I want to have a moving reference. So I'll write theta m is nothing but omega s mechanical into time plus delta m. So this delta m is the relative angle compared to the synchronously rotated reference frame, like that. So now if I differentiate this, I'll get omega Sm, T will be not there, and then d by dt. If I once again differentiate this is a constant now. Here T into this, it was there. So d2 theta m by d theta square is equal to d2 delta m by d theta dt square. So basically I can replace the theta m absolute mechanical angle with reference to fixed stationary reference to a relative mechanical angle with reference to a axis moving at a speed. So, so now if I go back to this previous equation, so this equation I can modify now. So let me do that. So I go to a new page. Into d2 delta m by dt is equal to tm minus t. Now I can multiply with omega m throughout this. Omega m is the angular velocity of the rotor. We have already seen j omega m dt delta m by dt is equal to tm into omega m minus t into omega m. So what is torque into omega? Torque into omega is power. Here also torque into omega is power. This is electrical power, whereas this is mechanical power. So I'll get j omega m d square, this is nothing but mechanical power minus electrical power. Okay, so now let's further continue this. So what I want to do is, this is moment of inertia multiplied by the angular velocity. So this one I can just denote it as m. So let m equal to j omega m. So therefore I'll get m into d square this equal to Pm minus Pe. So where m is the inertia constant. So I'm not doing anything very complicated. I'm just trying to simplify it. So inertia constant unit is joules seconds per radian. So this is a unit of that. So because you see here radians per second is there. So it will just second square per radian square like that will be there for J. So it will be like that. Let's continue. Now I also know what is the kinetic energy stored in the rotating kinetic energy stored in a rotating object. What is the kinetic energy stored in a rotating object? So that is nothing but half j omega square. This is the uh, this is the definition of kinetic energy stored in a rotating object. See, recall. So, what is the kinetic energy stored in a linearly moving object? Half mv square. So, what is m? Mass. So, in the place of mass, we are getting moment of inertia. What is v? V is the velocity of the object. So, here in the case of velocity, I am getting angular velocity. So, omega m is angular velocity, radians per second. That is angular velocity. So it is nothing complicated, just this is for straight line, this is for a rotating machine. Now j omega I already know that is m. So here I have just defined that. So here I am in j omega square. So I also know that kinetic energy is nothing but half into m omega m square. So from this also I can define what is m. So what is m here? 2 into kinetic energy stored divided by, sorry, the square will not be there, divided by omega m. So this is my definition of m. So we will come to it when we take up some example problems, we will come to it. So this is joules second per mechanical radians. So here I have also introduced another concept, another constant. That constant is called h. So this I just put a line. So there are two constants. So by the way, so I'll just put a line here. So this is m constant, and here I am talking about another constant called h. Typically, a manufacturer will provide this h. So how h is defined is h is defined as stored kinetic energy in rotor at synchronous speed in megajoules divided by rating of the machine in MVA. So what is the total stored kinetic energy? Kinetic energy already I have defined here, that is half j omega m square. Half j omega m square. So this is kinetic energy stored divided by S rated, complex power MVA rating of the machine. This is nothing but my H. And we should define it in such a way that the numerator is in megajoules and denominator is in the MVA, megavolt amperes. So interestingly, this unit is also equal to seconds. 1 megajoule by 1 MVA is 1 second. So now we can also find the relation between M and H. So again, that is just simple substitution. So you can find M is nothing but 2H by omega m. Just by comparison, you can know that. So now if I substitute this 2h by omega m into our main equation, that is what we had here. So let's call it as equation A. So then I'll get the swing equation as like this. That is 2h by omega omega m d2 delta m by dt square equal to mechanical power minus electrical power. So this equation again is in so by the way, here I forgot to mention, here it will be S rated also into S. So that S that was here will now come here. So what is the mechanical power divided by the rated power? Similarly, what is the electrical power divided by the rated power? Nothing but it will be the per unit value. So 2h by omega m d square delta m by dt square is equal to Pm in per unit minus Pe in per unit. So like this, I'll get a final swing equation. So this is the swing equation of a machine. Very important. Intuitively, we understand that any variation between Pm and Pe, delta will vary. But how exactly the delta is vary with respect to time is described by this second order differential equation, which is this 2h by omega m into all these things. Now, there is still some thing we will have to do. That is, I want to eliminate this delta m and then keep it as a just delta. So, what is delta m? Delta m is mechanical load angle. Now, I want to get electrical load angle delta, which is nothing but P by 2 into delta m. So, sometimes what happens, depending on the number of poles, so if the poles are 2, then mechanical and these are same, but then the electrical delta will be, so this is electrical delta, that will be a factor of P by 2 by n. So, if I substitute this here, then I'll get a P by 2 factor outside, and then I'll get something like this. Now, what is, I have to make one more substitution. So, let's call this as equation B and let's call this as equation C. Now, what is omega m? Omega m is the radians per second angular velocity of the rotor, mechanical angular velocity. So, same thing will happen if I do this. I'll get electrical omega, just omega. This is electrical omega, this is electrical delta, and these two are there. So, if I substitute this both equations C and D into this equation, so you will get like this 2h by omega into P by 2, okay, and then into D square into delta by dt square into P by 2. So this P by 2 will get cancelled out each other. So this is again in per unit, this is in per unit. So this P by 2 will get cancelled out each other. So I can now write 2h by omega into d2 by dt square equal to Pm in per unit minus Pe in per unit, like this. This is again the latest swing equation. There are different forms of swing equation. Now what is omega? Omega is nothing but 2 pi f. So 2h by 2 pi f. F naught may be synchronous frequency. So 2 will cancel each other. So I'll get h by pi f naught also into d2 delta by dt square equal to Pm minus Pe in per unit. So this is another formula. Okay, so let's solve an example problem so that we get more clarity on this. So any doubts up to here? Basically, our objective was to derive an expression for the variation in the load angle with respect to the variations in the powers. Any doubt up to here? We'll solve an example problem very shortly. We have any give you more clarity in what we are discussing. So the given data is like this. So 50 hertz, 100 MVA, 4 pole, synchronous generator. Has an inertia constant. So inertia constant means h. So h is 3.5 seconds. So system base, S base is nothing but 500 MVA. So you notice that the machine base is 100 MVA, whereas the system base is 500 MVA. Okay. So the electrical energy supplied is 0.16 per unit on system base of 500 MVA. This is the electrical energy supplied by the machine. This is also given. Now, therefore, under stability, what happens? Under stability, stable conditions, under stability, P mechanical equal to P electrical equal to 0.16 per unit. But what is happening is P mechanical is given 0.18 per unit. So even though the load is only, electrical output is only 0.16, mechanical energy input to the generator increased to 0.18. So as a result, what happens is the rotor will accelerate. So determine. First one is kinetic energy stored in the rotor. Second one is we have to determine kinetic energy stored in the rotor, and also we have to determine the acceleration. Acceleration of the rotor. So let's do that. So we know H itself is defined as kinetic energy stored in rotor divided by, so this is in megajoules, divided by motor rating, machine rating. In MVA. So this one I know, so I can find out the kinetic energy stored in the machine. So kinetic energy is equal to H into machine rating. 3.5 multiplied by 100. So this is 3.5 seconds. This is MVA. So this totally it will become 350 megajoules. So this much of kinetic energy is stored in the machine. Okay. So one thing we had completed. Now the next task is to find out what is the acceleration. So for finding out the acceleration, I have to find out what is the accelerating power. So what is accelerating power? So PM, so accelerating power is nothing but PM minus PE. So, but these are in per unit. So I don't want in per unit. So this is I want in actual value. That is PM per unit multiplied by S base minus PE per unit multiplied by S base. So I'll get 0.18 minus 0.16 whole multiplied by S base is 500. Sorry. So this is 0.02 multiplied by 500. So you'll get 10 megawatts. So 10 megawatts of accelerating power is there. Now you see, you just look at these two numbers. So there is a rotating mass. That rotating mass is having 350 joules of megajoules of energy. To that rotating mass I am giving extra 10 megawatts of power. So as a result, what it will increase its rotation. So to know that, we already have our equation. That is, just a minute. So we have our equation, that is m equal to 2h by omega n. So this is what was our definition, where m is the constant of inertia. So from this, what I can get? 2 into h is 3.5 and omega is nothing but 2 pi into m. But because I want to calculate the angle in degrees, instead of 2 pi, see what is omega m? Omega m is 2 pi into f. So whereas is 180 degrees into f if I want to do it in degrees. So that is pi radians is 180 degrees, so that is 2 into 180 degrees. So total I will get 360 degrees. Frequency is 50 hertz given in the question. So if I do this, sorry, into S rated is also there. So into rated power is 100 MVA for the machine. So if I do this, I'll get something like, so if I further simplify it, I'll get 3.5 by 90. So this is just a number. So this is what is my M. Now, but what I am interested is more about this quantity, that is, you know that d m into d2 by delta by dt square is equal to p m minus pe. So I am more interested about this term. So this m I can substitute here. So 3.5 by 90 into this will be equal to 10 here. Now if I further simplify this, I'll get the second derivative of delta is nothing but 900 by 3.5, which is nothing but comes to around 257 degrees. So this is electrical degrees, this is per second square. So because this is acceleration, that means the rate at which the delta is increasing is this much, 257 degrees. So now I can further ask, although it's not asked in the question. So acceleration of rotor is nothing but 257 degrees per second square. So I can now ask a question. See, this Pm equal to 0.8 and Pe equal to 0.16. So this condition lasts for, let's say, 60 milliseconds. For 60 milliseconds, this balance is changed, and then later on again, so Pm equal to Pe equal to 0.16. So momentarily I am increasing the mechanical power, and then again I am getting it back to the normal value. So during that time, find out the acceleration in delta, or final value of delta, or the change in the delta. So time is given, acceleration is given. So I can find out that. Of course, you should also know what is the velocity. So the velocity is actually omega s. So anyway, so since I'd like to show another problem. I'm just stopping it here. This is just an additional idea I wanted to give. So what is required to find here? Kinetic energy stored we found, and acceleration of the rotor also we found. So before I go forward, just I'll give you a couple of minutes. Any doubts about this question? The main thing in this problem is how to handle this H. So H is given in 3.6 seconds, and question is asked what is the kinetic energy stored in the rotor. So the definition of H is kinetic energy stored in the rotor by machine rating. So H is given, machine rating is given. So I can find the kinetic energy stored in the rotor, 350 megajoules. Then another part of the question was, what if there is a step change in the mechanical input? So if there is a step change in the mechanical input, then there should be a positive change in the this one. So like if you look at this equation, if mechanical input is more than the electrical input, then this will become positive. That means it will accelerate. Similarly, if mechanical input is less than electrical input, then right side is negative. So this also will be negative, and this will decelerate. And then just to find m, we had this one, so we found m based on that. We had this relation 2h omega m into s. So now finally I got this equation. So in this equation, so like look at this equation. And finally this equation I got, that is delta, that is this one. So this equation is a differential equation, and to solve this differential equation, you would require some kind of solver. So that's why the problem was stopped here. Okay, so let's continue to. I'd like to explain something more. Where just a minute. I'm now coming out of the machine, and then I'm connected to an infinite bus. So this is one angle 0 degree. This is some reactance X, and this is my EMF induced, and this is my delta angle delta. So consider a generator whose output voltage is this one. So remember, sometime back we solved a problem, two sources connected by a single resistance, single reactance. So two sources connected by a line. So that is what is this one. So here I am interested in calculating of what is the active power leaving this machine. What is the PE, electrical power. So to know the electrical power, first is I can find what is the current. So let's define current as I. So what is the current? Current is nothing but EMF E angle delta minus 1 angle 0 degrees or V angle 0 degrees. So let's consider this as V. So divided by X. So X will be Jx actually. So it will be reactance. Now this here I am not considering the resistance. So only reactance I am considering. Now this is the current. So or I'll get E by X, and the angle will be delta minus 90 degrees. Because this J is there, it goes up, it becomes minus 90 degrees. Similarly, I'll get V by X, and the angle will be 0 minus 90 degrees. So this is my current. Now, what is the active power being output of this? What is the active power that is being fed into the grid here? So active power is nothing but terminal voltage into current. So V angle 0 degrees into I conjugate. Sorry, not just active power. I am interested in the complex power at the infinite bus. Here, what is the complex power? So complex power is nothing but V into I conjugate. So that's what I will do it here. So that is V angle 0 degrees into I conjugate. So the conjugate of the above I. So V angle 0 degrees multiplied by, so E by X will remain E by X, and this angle will become 90 minus delta, just the reverse of this angle, minus V by X, and this angle will become 90 degrees. So this is the conjugate. So after applying conjugate, now I multiply by V. So I'll get EV by X into 90 minus delta as an angle. Similarly, here I'll get V square by X, and the angle is 90 degrees. This is complex power. So I am interested only in the real component. So that is PE, electrical power. What is the real component of this? Nothing but EV by X cos of 90 minus delta minus V square by X cos of 90 degrees. So cos 90 degrees is 0. So this term will be equal to 0. So finally I will get this. So electrical power is nothing but EV by X into cos 90 minus theta is sine delta. So like this. So this is nothing but the power equation. Now if I fix the values of E, that is magnitude of E, magnitude of V. So during that small period, 10 milliseconds, I am assuming if the voltages are not changing and reactance of the line is also fixed, then I can write P is nothing but P maximum into sine delta, like this. So what is the electrical power output? Is nothing but the maximum power, some maximum power defined by EV by X multiplied by sine delta. So this is the thing. Now this one I can show it is graphically. So how to show graphically? So I have x-axis. On x-axis I will show delta. On y-axis I will show P or power. So sine delta, it is like this. So some maximum value is there, that is P max, and depending on the delta it will be there. Now this value corresponds to 90 degrees and this value corresponds to 180 degrees. Now imagine that there is a machine, mechanical power is input and electrical power is output, and then this machine is maintaining some delta. So if I draw a horizontal line like this, so this is mechanical power, and so this is PM, and whereas this is PE. So PM equal to PE is this point, and PM equal to PE is also this point. So let's denote this as delta naught. So out of these 2 points A and B, which point is stable? So A is stable, B is unstable. So what is the reason? The reason is like this. Let's say I am operating at delta naught. Now due to some disturbance, my mechanical power input has increased. So if your mechanical power input has increased, then this line will go up. When this line goes up, this A point will move upwards. When A point will move upwards, because it's a sine curve, even the electrical power also increasing. So any increase in mechanical power results in increase in the electrical power, thereby stability is maintained. So I can go to this new point and A dash can be my stable point. Or if the PM comes back to normal value, PE also will come back to normal value. Again I will come back to this and delta naught will be my stable point. So that's why I am saying this point is stable. Whereas here what happens, you notice, if I increase PM, I will slightly go up. So, but then here the delta is decreasing. So here PM is increasing, delta is increasing, and then this is decreasing. Here delta will increase. So when delta is increasing, you will get another situation where increase in PM will result in reduction in PE. So actually I should show like this, increase in PM will increase the delta and it will reduce the electrical power, and this is unstable. So all the points, this is 90 degrees, on the left side of this are stable points and on the right side of this are unstable points. So this is what is known as a power angle curve. So the power angle curve comes out of this expression. So any doubts based on, so you should operate the system such that the delta, so if you have a system like this, there is an infinite bus or this is a grid. You want to send power to the grid, this delta you should maintain such that it is not more than 90 degrees. So if this delta is 110 degrees, then you are unable to send the power to the grid. This delta should be all the time below 90 degrees, below the stability limit. So that is what is the point that we learn from here. Any doubts based on this? Problem, that is one of the important things. And also I will try to simulate the swing equation and then I will show it to you. So the next class will be on Thursday. So, and that will be the final class according to your timetable. But I would also like to take one more class online, that is I'll just record the video and I'll share the lecture with you. So kindly prepare this. So email ypradeep@iith. So what I'll try to do is the doubts can be from any part of the course. If you have any doubts, kindly send them mail.